Hello all, welcome to this video on distributed computing. Today I'll be talking about Ricart Agrawala algorithm in distributed computing. Mutual exclusion is a fundamental problem in distributed computing systems. Mutual exclusion ensures that concurrent access of processes to a shared resource or data is serialized, that is, executed in a mutually exclusive manner. Now, mutual exclusion is used in distributed file systems for locking of files and directories. It can also be used for accessing objects in a safe and consistent way to ensure that at most one server has access to object at any point of time. It is also used for server coordination where the work is partitioned among servers and the servers coordinate using locks. In industry, Google's locking service called Chubby uses it. Many cloud stacks use Apache Zookeeper for coordination among servers. Now let's look into the problem statement for mutual exclusion. Critical section problem is a piece of code at all processes for which we need to ensure that there is at most one process executing it at any point of time. Each process can call three functions: the enter function to enter the critical section, access resource function to run the critical section code, and the exit function to exit the critical section. Now, there are different ways of implementing mutual exclusion. Now, if we are dealing with a single OS where all the processes are running in one OS on a machine or a VM, then we can use solutions like semaphores, mutex, condition variables, monitors, etc. When it is in a distributed system, the processes communicate by passing messages, and we have to guarantee three properties. The first one is safety, which means that at most one process executes in the critical section at any time. Second property is liveness, which states that every request for a critical section is granted eventually. This property states the absence of deadlock and starvation. Two or more sites should not endlessly wait for messages that will never arrive. In addition, a site must not wait indefinitely to execute the critical section while other sites are repeatedly executing the critical section. The third property is ordering or fairness. Requests are granted in the order they are made. So each process gets a fair share to execute the critical section. Now we'll look in detail into the mutual exclusion in distributed systems. In a distributed system, we cannot use shared variables like semaphores. Now, how do we support mutual exclusion here? The design of distributed mutual exclusion algorithms are complex because these algorithms have to deal with unpredictable message delays and incomplete knowledge of the state of the system. To solve the synchronization problems in a distributed system, we need to provide distributed semaphores. There are three schemes of implementation. One is the centralized algorithm, the other is a token ring approach, and the third is a distributed algorithm. Now let's look into the system model. Each pair of processes is connected by a reliable channel such as TCP. Messages are eventually delivered to the recipient and in first in first out order, and the processes do not fail. We'll start with the centralized algorithm. Here we elect a central master or a leader using one of the election algorithms. The leader keeps a queue of waiting requests from the processes who wish to access the critical section. And there is also a special token which allows its holder to access the critical section. The actions that can be performed by any process in the group are the enter action, which is used to send a request to the leader and wait for token from the leader, and the exit action, which will send back the token to the leader. Now looking into the leader actions, on receiving a request from a process PI, if the leader has the token, then it will send the token to the process PI, or it will add the process PI to its queue. Now, on receiving a token from process PI, if its queue is not empty, then it will dequeue the head of the queue, that is, dequeue the process, say PJ, and send the process the token. Otherwise, it will retain the token. Now, looking into the analysis of the centralized algorithm, when checking the property of safety, where there is at most one process in the critical section, that can be ensured here because there is exactly one token. The second property of liveness, that is, every request for critical section being granted eventually, is also followed here. With n processes in the system, the queue has at most n processes. If each process exits the critical section eventually, and if there are no failures, then liveness is guaranteed. Now, the first in first out ordering is also guaranteed in order of the request received at the leader. Now, analyzing the performance of this algorithm. Efficient mutual exclusion algorithms use fewer messages and make processes wait for shorter durations to access the resource. For that, we use three matrices. The first being bandwidth, which is the total number of messages sent in each enter and exit operation. Then we have client delay, the delay incurred by a process at each enter and exit operation when no other process is in or waiting. Then we have synchronization delay, which is the time interval between one process exiting the critical section and the next process entering it, when there is only one process waiting. Now, when we look into the bandwidth property, we will see that we need two messages for enter. That is, one is to send a request to the leader and other is waiting for the token. And we need one message for exit. Now, looking into client delay, we need two messages. One is for the request and one is the granting of the request. And for synchronization delay, we need two messages. One is for the release and one is for the granting of it. But the problem in this algorithm is the leader is the performance bottleneck and it is also the single point of failure. Now we move on to the next algorithm, which is token ring algorithm. Here we have n processes organized in a virtual ring. Each process can send message to its successor in ring. And there is exactly one token. Here also we have the enter operation, which will wait until it gets the token. And then we have the exit function, and it can be executed only when there is a token present. It will pass the token to the ring successor. If it is receiving a token and if it's not currently in the enter function, then it will just pass on the token to the ring successor. Now, this is an example of how the token ring algorithm works. We can see that here the process P3 currently has access to the token. So it has access to the critical section. Now, after exiting the critical section, it will pass the token to its neighbor. Now, after releasing the token, it cannot access the critical section anymore. Now, the token is acquired by the process P32, so it can currently access the critical section. Now, let us go through the analysis of this algorithm. Now, we can see that we are going to verify the safety property in the first case. So here we see that there is exactly one token, so the safety property is guaranteed. Now looking for the second property, which is liveness, we see that the token eventually loops around the ring and reaches the requesting process and there are no failures. Now when we look into the bandwidth, we'll see that per enter function, there is one message by the requesting process, but there can be up to n messages throughout the system. Also, there is one message sent during the exit function. Now, when looking into the client delay, there can be 0 to n message transmissions after entering the enter function. Now, going through the best case for client delay, it is a case where the process which is requesting the critical section already has the token. Suppose P32 wants an access to the critical section. If the token reached P32 at the same time, that can be considered as the best case. Now, when looking into the worst case, we see that that is when it has just sent the token to its neighbor. So, in this case, we have seen the token was first held by P3, and after it exited the critical section, it sent it to 32. Suppose after releasing the token to P32, there was a critical section requirement by P3. So now if P3 has to access the critical section, the token will have to traverse through the entire ring. So that is the worst case scenario for a client delay here. Now when looking into the synchronization delay between one process's exit from the critical section and the next process's enter, we see there can be between 1 to n minus 1 message transmissions. Now here the best case would be the process in the enter function is a successor of process in the exit function. That will mean that if P32 wants the critical section access, that is it has to go through the enter function, and if P3 is going to the exit function because it is going to release the token after its use. Now this can be called as the best case. The reason is P32 has a requirement to enter the critical section. At the same time, P3 is releasing the token to P32. So that is the best case. Now if we are looking into the worst case, we will see that the process that is getting into the enter section is a predecessor of the process in the exit function. It can be the other way around. That is, P3 actually is getting into the enter function because P3 has to access the critical section, but P32 is in the exit phase. So if P3 needs to access the critical section, this token has to go through the entire ring again to reach P3. So that is the worst case scenario here. Now let us look into the issues that we face in this algorithm. If the token is lost, it needs to be regenerated. The detection of the lost token is difficult since there is no bound on how long a process should wait for the token. If a process can fail, it needs to be detected and bypassed. Now, when nobody wants to execute the enter function, processes keep on exchanging messages to circulate the token. Now, when we look into the client or synchronization delay to access the critical section, it is still big O of n in this ring-based approach. So, we are looking for a model in which we can make this faster. Now, we are seeing the system model for that particular solution where each pair of processes are connected by reliable channels such as TCP. The messages are eventually delivered to the recipient and in first in first out order, and the processes do not fail. Now this solution is called the Ricart Agrawala algorithm. Now this was invented by Glenn Ricart and Ashok Agrawala. It is a classical algorithm from 1981. Here there is no token. This algorithm uses the notion of causality and multicast. This solution has a lower waiting time to enter the critical section than the ring-based approach. Now, when looking into the key idea of this algorithm, a process at the ender phase of this algorithm, what it does is it will multicast a request to all the other processes. So the request will be in this format where T will be the current lamp or times time at process Pi. Now what this process will do is it will wait until all the other processes have responded positively to this request. And now these requests are granted in the order of casualty. Now this request T, Pi is used lexicographically. That is, the Pi in this request will be used as a tiebreaker, since there can be cases where the timestamps can be the same because Lamport timestamps are not unique for concurrent events. Now we look into the messages used in this algorithm. So here in the ender function at process Pi, what we do is we'll set the state of the process to wanted. Then we'll multicast the request in this form containing its timestamp and process ID to all the processes where, as we saw, Ti is the current timestamp at process Pi. Then this process will wait until all the processes will send back a reply. And after that, this process will change its state to held and enter the critical section. Now, on receipt of a request TJPJ at Pi, that is a request from the process J reaches the process I. Also, in this case, I will not be equal to J. Here what it does is, it will check if the state is held or if the state is wanted and if the timestamp of Pi is less than Pj. So if the timestamp of Pi is less than Pj, it means that the process Pj happened after Pi. That is why Pi is having a lesser timestamp. So if that's the case, then the process will add the request from Pj to its local queue of waiting requests. If it's the other way around, then it will send a reply to the process Pj. Then at the exit function at process Pi, it will change its state to released and it will send a reply to all the queued requests. Now let us look at an example on how this algorithm works. So as we discussed before, initially the process which wants to access the critical section will change its state to wanted and it will send a request message to all the other processes in the system in the format containing its timestamp and process ID. Timestamp is 102 and process ID is 32. Next, what happens is all the processes will reply with a reply message. Then what happens is P32 will change its state to held so that now it can access the critical section. So after some time, both process P12 and P80 are interested in accessing the critical section. So first what they do is they will change their state to wanted and they'll send a request message containing their process ID and timestamp to all the other processes in the system. Now, both P12 and P80 receives reply from P6, P5 and P3. And next what happens is P32 is actually in the held state. So the requests from P12 and P80 will be added in its queue request. And then what will happen is these two processes, that is P12 and P80, are also requesting each other for access to critical section with its request. So here, as what it was discussed in the algorithm, what it does is it will check the timestamp. So as you can see, P12 has timestamp 115 and P80 has timestamp 110. So P80 happened before P12. So clearly P80 has an advantage. So what it does is it will add the request from P12 to its queue request. Then what will happen is P12 will respond with a reply message to P80. Now P80 has received a reply from 4 messages. Now the request left is that from P32. So after some time, P32 will release its access to the critical section. So it will change its state to released, and it will multicast its reply to both of these processes because they gave a request for access to critical section. Now since P80 received reply from all the processes, it will change its state to held so that it can now access critical section, and its queue request will contain the request from P12. So P12 will still be in the wanted state waiting for P80's reply. Now let us analyze this algorithm. Now looking into the safety property, here two processes Pi and Pj cannot have access to the critical section at the same time. Now if that is the case, then both of them would have to send a reply to each other. That is the case we saw here between P12 and P80. Both of them requested for the critical section at the same time. But what happens there is we are comparing their timestamps. So if both of them are replying each other, then it should be like Ti is less than Tj and Tj is less than Ti, which is a contradiction clearly. Both of them happening together is not possible. So the safety property is ensured here. Now there can be a case where Ti is less than Tj and Pi actually replied to Pj's request before it created a request for the critical section. So that will seem like both of them will be approving each other's request. But again, according to the casualty property and Lamport timestamps at Pi, the condition can be satisfied only if Ti is greater than Tj. But we already saw Ti is less than Tj. So that is again a contradiction due to which the liveness property is ensured here. And in liveness property, we can have a worst case scenario where the process will have to wait for all the other n-1 processes to send a reply to itself. The ordering property is also ensured here by the fact that the requests with a lower Lamport timestamp are granted the access earlier. Now when we look into the bandwidth, we can see that it is 2 into n-1 messages per enter operation. So one set of n-1 messages will be the n-1 unicast messages for that multicast request sent by the process and the n-1 replies for that. So we need to send only n messages if the network supports multicast, which means there will be only one multicast message plus n-1 unicast replies for that. Now for exit operation also we need n-1 unicast messages. Now if the network supports multicast, then we need only one multicast message. Now when we look into the client delay, it is 1 round trip time and the synchronization delay is 1 message transmission time. That's all for now. Thank you for watching.